Hello, everyone. Welcome back to College Algebra. We are still in Chapter 1, the properties of real numbers. In this section, though, we are continuing this same section of operations of real numbers. We have done addition and subtraction, we have done multiplication and division. We are moving on to exponents and square roots. This will broaden our access to types of numbers and how we can use them, how we can access them, how we can manipulate them, and other cool stuff down the line. So, part 3, exponents and roots. I don't have square roots written down, but that's fine. Roots, because they are roots, and we'll get into that. So, what is an exponent? An exponent is a number that increases exponentially or without bound really quickly. It gets very large, positively or negatively, very quickly. So, for example, here's a very simple example. What if I just simply doubled numbers? So, 1 plus 1 is 2. 2 plus 2 is 4. Plus 4 is 8. Plus 8, 16. Plus 16 is 32. Plus 32 is 64. Plus 64 is 128. You see how fast we got to the hundreds. We went from 1 in just a few short seconds. We already got to 120. And with 3 more numbers, I can get into the thousands. So exponentially is a number that increases doubly without bound, or doubly without bound. But exponents are not a property of addition. They are a property of multiplication. So, what do I mean by that? We have a number times itself a certain number of times. So, for example, it wouldn't be 2 plus 2 equals 4 or 4 plus 4 equals 8. That wouldn't be a true exponent. This was just an example of showing what an exponent could look like. What an exponent really is a number times that same number, however many times we may want. So, for example, let me erase some of this because I don't want to scroll down just yet. If I said 3 times 3, we know 3 times 3 equals 9. But there's a special way of writing that. I could write 3 to the second power equals 9. So what this means is I'm simply multiplying 3 to itself 2 times. And you can do this with any number. Let's use another color. I could use 2 squared, which simply equals 2 times 2, which equals 4. We could use 4. 4 squared equals 4 times 4 equals 16. 5 squared equals 5 times 5, which is 25. Any number works. 10 squared equals 10 times 10, which is 100. An exponent is simply a number multiplied to itself a certain number of times. So we've been using this second power. We can also use other powers. Say we could use 2 to the third power, which simply means 2 times 2 times 2, which equals, we got 2 times 2 is 4 times 2 equals 8. We could write 3 cubed, which is, and we're saying cubed. I didn't explain that. We're saying cubed. So square means 2, cubed means 3. You don't have those are the most common powers we see. So there's special names for them. That's why we call it squared or cubed. They're the most common. However, you could just simply say to the second power or to the third power. So 3 to the third power would equals 3 times 3 times 3. And what is that? 3 times 3 is 9 times 3 equals 27. And that goes with all numbers. 10 to the third power equals 10 times 10 times 10. What is 10 times 10? That is 100 times 10 gives us 1,000. See how easy that is? All it is that you're just simply multiplying the same number to itself. It has to be the same number. Let's give a formal definition to the exponent. A formal definition. We are going to use a letter rather than a number. So, say we have a to the n power. If a is a real number and n is a natural number, so that's our condition. We have to have a as a real number. Remember from our very first video, what is a real number? And n is a natural number. Remember what the natural numbers are. The natural numbers are any positive number greater than 0. That includes 1, 2, 3, 4, all the way to a billion plus more. So if a is a real number and n is a natural number, then a to the n equals a times a times a times a all the way to times a n times. That is our definition of an exponent. All this says, however many times, whatever the number of n is, that's how many times we multiply a to itself. So a to the nth power equals a times a times a times a, as many as n times. And we already did a few examples, so I just wanted to express what exactly an exponent is. And it's super easy. So, as an exponent, notice how I said a has to be a real number. What includes real numbers? We have positive numbers, such as 5 squared, which we already settled as 25. That's not 25. You Come on. 25. This also includes ratio numbers, such as 2 over 3 squared. Now, notice how the power, the exponent, is outside of the parentheses. That means we have to apply the exponent to both the numerator and the denominator. So 2 over 3 to the second power equals, what is 2 to the second power is 4, and 3 to the second power is 9. What if we had 2 squared over 3? This would have simply become 4 over 3. And if we had 2 over 3 squared, that would have become 4. Nope. That would have become 2 over 9. See the importance of the placement of the exponent. If the exponent is outside of the parentheses, you apply the exponent to everything. Everything. That is very important. Everything inside the parentheses. If it is not inside the parentheses, you simply apply the exponent to whatever number the exponent is attached to, whether it be the numerator or the denominator. What if our exponent had a sign? if we have a number such as, okay, since we in the definition we used a, what if a equals -2? So when we have a to the n, say we need to find a squared. Okay, what is a? A is -2. So let's apply our -2 and then squared. Notice how I kept the -2 inside the parentheses, because whatever a is, you have to put it inside the parentheses. So -2 times -2. Remember our rule of signs for exponents. -2 times -2, or a negative times a negative, always becomes a positive. So -2 squared, or -2 to the second power, equals 4. Now, what if we had -a squared, and let's say a equaled 2? You with me? Say we have -a and a equals 2. Remember, this 2 is being applied, or this exponent, this second power, is being applied to this a. It's not being applied to the a and the negative sign. That means we do not square this -1, because we are not applying it to that. It is simply attached to this a. So if a equals 2, we have -2 squared. That means we simply have to square this 2. So what is 2 squared, or 2 to the second power, equals 4. So because we did not affect this negative sign with the square, we carry it over. This becomes -4. If we have a negative number being squared, it will always give us a positive number. Remember though, what if we had a cube? Or what if we was multiplying 3 times? Remember, 3 was a type of odd multiplication problem. Let's use another marker. Say we had a equals -2, and we had a cubed. So let's apply our -2 cubed, or to the third power, equals -2 times -2 times -2. What is -2 times -2? That is 4 times -2, which gives us -8. So -2 to the third power equals -8. So if you have a third power, you're going to, and your number is a negative number, you're going to end up with a negative number. But if you have a second power, you're going to have an even number. This follows for all exponents. If you have an even number, if a equals a negative number, then a squared, a to the 4th, a to the 6th, a to the 8th, it doesn't matter. It will be a positive number. But if a is a negative number and you have a to the 3rd, or a to the 5th, a to the 7th, a to the 9th, or any other odd number, it's going to be a negative number. That even odd situation follows throughout all of algebra and calculus. So this is something to remember. So squares and cubes. I covered squares and cubes a little bit already. Let me use baby blue. So squares and cubes. What's a square? Well, a square is that, right? What's a cube? A cube is something like this, right? Kind of three-dimensional like. What does this have to do with exponents? Super easy. You can use it to find the area of this surface. So, say for example, this square was 3 inches long on each side. I could add, and if I ask you what is the area or how many inches does this square cover, you would say, well, it covers 3 by 3 or 3 squared, which would be 9 inches, right? That'll be 1, 2, 3, 4, 5, 6, 7, 8, 9 inches. It will cover 9 square inches. And you will write that as inches squared. 9 inches squared. Now, what about this cube? How do I find the area of this cube? Well, let's use a different number. Let's say we have 5. So we know the cube is 5 inches on the side, on the bottom, 5 inches tall, so 5 inches wide, 5 inches tall, and 5 inches long or deep. So 5 inches right here, and right here. The area of a cube can be found by taking the cube of this number or of this area. So we have 5. I want the other. Why do I have that number? Give me this. So we have 5 cubed. Because we have 5 times 5 times 5 will give us the area of a cube, which is 125 inches. That's a square. Cubed. So the area of a cube will be 125 inches cubed if all 3 sides was 5 inches. That's the relation between squares and cubes and exponents. And when you study like geometry and things like that, you'll find a lot of use for something like this. A lot of carpenters or builders and different types will use this type of aspect when preparing to build a house or a store or something. Just like with addition and subtraction, multiplication and division, exponents also has a type of inverse or undoing of itself. It's called the root of a number. The root of a number is a number that can be divided by its not divided. That can be how would you say this? Let's do it this way. I have a number. Say I have 25. We know that 5 squared equals 5 times 5 equals 25. The square root of a number gives us the number multiplied by itself twice to give us this number or this principal root. When you are asked to find the square root of a number, you are asked to find its principal root. Usually you want a whole number such as 5. So the symbology used in square roots looks a little bit like the long division symbol. If you've seen long division, it looks something like that. So like 9 divided by 3, you know. But the radical is what it's called. The square root symbol looks like this. So square root of 25 equals 5. This is called a radical. And this is called your radicand. And we'll cover that when we get into the lesson when we really need to break these type of things down. But we just want to know the basic square roots right now. All you have with the square root is you're asking to find what number multiplies itself. What number multiplied by itself twice will equal 9. And we know that's 3 because 3 times 3 equals 9. The square root of 16 equals 4. You are simply asked to find what number can be multiplied by itself to give this number. That is called your principal square root. I probably misspelled that. I hope not. That's your principal squared root, because you want to know what full number, a whole number, will give us this number under the radical symbol or the square root symbol. And just like with exponents, say we had a square root that had a fraction inside of it. Say we have 9 divided by 4. 9 divided by 4. What is the square root of 9 divided by 4? You would solve it just like we did with the exponent. This would give us 3 divided by 2. The square root of 36 divided by 49. Some big numbers. But if you know your principal square roots, I believe, let me see if I can find one. So I couldn't find one. I used to have a couple of composition notebooks, and those composition notebooks, on the front or back cover of the notebook, you would have a multiplication chart such as this right here. And if you look at down the center line, you notice that you'll have the multiplication charts for the double numbers. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. Or 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared 16. 5 squared 25. 6 squared 36. 7 squared 49. 8 squared 64. 9 squared 81. 10 squared 100. 11 squared 121. 12 squared 144. Most common composition notebooks will have the multiplication table up to 12. And so you find this, you can follow this middle diagonal line, and that is your principal square roots of these numbers. So the principal square root of 144 will be 12. The principal square root of 121 is 11. So it'll follow, you could follow something like this. If you, for the basics, learn your principal square roots, it'll help you to have these type of things memorized. Try to find my, here we go. So, with that said, these numbers might look big, but you can recognize that these are easy square root numbers. The square root of 36 is 6, and the square root of 49 is 7. Not hard at all. Super cool, super easy. One last part to cover. We have cube roots. Just like with squares, just like how we can have 2 squared, we also had 2 cubed. Same thing goes for square roots. We had the square root of 2, or, so we knew the square root of 2 was 4. This cube root of 2 was 8. We could have written the square root of 4, or the cube root or third root of 8. What number times itself 3 times will give us 8? And we know 2 times 2 times 2, or 2 cubed. So square root of 4 is 2. The cube root of 8 is 2. The cube root is simply just a higher order of root, and they cover just like exponents do. So let's go a little higher. Say we have 2 to the 4th power, which equals 2 times 2 times 2 times 2, which we have as 2 times 2 is 4, times 2 is 8, times 2 is 16. So we have 16. 2 to the 4 equals 16. That means the 4th root of 16 equals 2, right? Not hard. If I had the cube root of 1000, that equals 10, because 10 cubed equals 10 times 10 times 10 equals 1000, right? All it is simply they're asking you to find the principal root or this principal cube root of 1000. All it is. So that's it for exponents and roots. The next lesson, we're going to cover the order of operations. And then we will finally be able to move on from this basic part of the prerequisites of algebra and start moving on to the more difficult parts of the prerequisites. That way, when we tackle college algebra as a whole, we'll be able to plow through it because we will have the basics memorized and mastered. So, exponents, roots, techniques of multiplication is what they are. There we are. Techniques of multiplication. I hope you enjoyed this lesson. I hope you've learned something. If not, maybe refreshed your memory, maybe. After a few more lessons, I'm going to start producing side videos that will have a type of just pure problems to do. So it might be like an hour and a half, 2 hour video, where I'll just be working problems. I don't want to do it for these because there's only so much you can do when we are not using variables and we're not using combined techniques, which is where the beauty of mathematics really starts to shine. So when we begin to move on a little bit, when we get done with the exponents and we get done with the radicals and we can move on to, say, polynomials and factoring and complex fractions, I'll start producing those type of videos as a side so that we can all work together. I'll show one problem. You could pause the video, do the problem, and then unpause it and see if you came up with the same technique, same answer as me, or did you use the same technique as me? Because sometimes there's multiple routes to the same answer. So, with that said, the next lesson, order of operations, we will finally move on from the basic stuff. See you there.